Cool, thank you very much. So today I'll be talking about local and universal changes, sort of explaining precisely what I mean by this, and two particular applications, namely global terrorism and, of course, COVID-19. I'm affiliated with, in addition to the University of Bristol, the Harbour Institute for Mathematical Research, and much of the work I'll be talking about today was in partnership with many of my colleagues at IMA, and it would be churlish of me at this point not to give thanks to each and every one of them. They know who they are. So without further ado, I'll talk a little bit more about the flavouring of what we did with respect to COVID, and then talk a bit about the mathematics and the methodology which informed our initial approach. So back in the mists of time, otherwise known as the beginning of June, several of us at IMA were approached by the Cabinet Office to think about balancing three particular considerations with respect to the pandemic and how they may be affected by non-pharmaceutical interventions, or NPIs, as I shall refer to them for the remainder of the talk. So these particular considerations, which I've very crudely represented on this slide, were health, the economy, and well-being. And we were instructed that we could be quite flexible within this. We could choose to focus our attention on one of these three or two or whatever. But really, the aim of the game here and the Holy Grail was to come up with some way of quantifying the effect of an NPI on its relaxation or its strengthening, and what it would do to the economy on on one scale and health on another scale, and well-being if that was something we felt we could measure. We sort of realized fairly quickly that our USP here really lay in the economic sphere. This was partly because if we're thinking about health, as we've seen from the fantastic talks earlier today and from experience from RAMP and so forth, we knew there were many people thinking about the health angle of this. So we decided that we weren't too sure what we specifically would be adding. And likewise for well-being, the existing data sets that were focusing on this sphere at the time of asking at the beginning of June really weren't all that developed. So there was a YouGov poll that's been conducted since the end of April that has really quite nicely tracked people's sentiments throughout the pandemic. And this is something that I think if we were to undertake the analysis now would be really quite interesting. But at the time of asking at the beginning of June, given that NPIs really hadn't shifted all that much throughout the sort of end of April, beginning of June period, there really wasn't an awful lot that we could feasibly say. We thought a priori that would be useful with regards to that particular aspect of things. So the economy was really where we're focusing. And the game here, given that there is an additional problem thinking about the economy, is how we can appropriately proxy it, how we can appropriately measure the economy in a sort of a high frequency fashion, to be able to say meaningful things about various relaxations or strengthenings of particular NPIs, particular policies. So we might a priori think about using unemployment figures from the ONS, but clearly they're just quarterly or monthly in the very best cases. Whereas other data of higher frequency, so for example, credit card usage data, we're going to be needing NDAs and all sorts of things, and for various reasons to do with communication and sending information from various places within the organization and so forth, it was more useful for our clients that we were able to do this using open source data. So the game here is to try and proxy the economy using a high frequency open source data set. And some of the candidates that I'm about to show you should look very familiar indeed. The first of these was data from the Entsoe transparency platform. So Entsoe is an acronym which has temporarily slipped my mind, but it catalogues electricity usage across a number of European countries. In particular, you can get data on forecast load and actual total load for each and every country in the EU and some countries just outside the EU from the beginning of January 2019 to the present. So for example, for the UK, you can get half-hourly data. For many countries, you can get at least hourly data. And I think Germany records data every quarter of an hour. So that was a useful data set that we were there to keep in mind with. Other data sets that were in the mix, and as mentioned, one of these is incredibly familiar from Rita's talk, Google mobility data, which measures changes in mobility from a baseline from the 18th of February, I believe, although Rita may want to correct me on that, each day in 6 contexts, which again Rita was talking about in his previous talk. And we were also thinking about incorporating Google Trends data with particular focus on search terms such as unemployment benefits or furlough. And I don't know how well you can see this, but this is a plot looking at the terms unemployment benefits and furlough in the United States. So in early March, we can see that both terms sort of surge up, and then one of those drops off. I think, yes, so furlough drops off after a month or so, but unemployment benefits are still something people are searching for months later. So all of these were seen as useful, but on the other side of the equation, we did some way of tracking all these NPIs, just so that we had something to compare our results to at the very least. So for this, we use the data compiled by the Blavatnik School at Oxford, which gives a record of when policies were enacted and how severe each policy was. And what I'm showing you here is a plot of the stringency index in each country, a stringency index being recorded from 0 to 100, 0 being least strict, 100 being most strict. So I don't think any country actually got to 100, but this is in theory every single policy that could be enacted to tackle the pandemic in the list of possible space of policies is enacted to the fullest level of strictness. But this is really sort of to try and collate various different policies. So school closures, workplace closures, travel bans, etc. And in general, in the data set, we see for each of these policies a score from 0 to 4, where a score of 0 denoted that policy was not in effect at all, and a score of 4 was that policy was in effect as strictly as possible. So to give you an example, if you have thinking about the school closure policy, a score of 0 implies that schools are entirely open. A score of 4 is they're basically entirely closed. So the UK got to a score of 4 for schools, even though even during the height of the pandemic, certain children were still going to school. So just to try and add a bit of flavour, I will show you a graphic with this picture changing. So this is for the 28th of October. I'll try and equally as seamlessly show you what this looks like over the course of the year for the whole world. And I can also hover over and show you the stringency index. So back on the 22nd of January of this year, the UK had a score of 5.56 out of 100. So if I would just show you how this evolves over time, we can see that in February, very few countries had done much at all. But then during March, there's basically a surge of policies being put into place with the stringency index ramping up almost everywhere. But even at its strictest, the UK is something like 70, 74, 78. And it's sort of at the point in June, you could see where the UK was sort of at a stricter stringency than many of the other countries in the EU and well, in Europe and in the West in general, that we were really interested in seeing what we could alleviate to have the greatest economic impact while keeping people safe. So there we are right now on December well, this is yesterday, December the 14th, but that hopefully should give a flavour of exactly what the data are showing. So I'll just stop sharing my screen here and go back to the slides. I'm sure there was a more technologically advanced way of doing it, but why make things simple for myself? Okay, so this is the backdrop for things, and as mentioned, we have the Entsoe energy data set, and that's what I'll be talking about predominantly today. I have some things I could say about the other data sets as well, although as Rita's talked quite eloquently, well, very eloquently about the Google mobility, I feel like I would be stealing that wheelhouse a little bit, so I'll just stick to Entsoe for now. And also some pertinent reasons why Entsoe is interesting and useful. As mentioned, it's very high frequency. There's one measurement per half hour for the UK, and you have measurements quarter hourly in many other countries, and hourly at least almost everywhere in Europe. Data for a number of European countries, so we can have a reasonable comparison with countries that were slightly ahead of us in terms of the pandemic curve and in terms of NPIs, locking down, unlocking, some that were behind us. And we also have data from an entire normal year's worth of energy usage. So this allows some baselining and correcting for seasonality, because that is important, as I will show you on this plot. So if I were to show you this plot of 2020, and if I were to cover up the year, you may well conclude that there is a certain amount of seasonality going on. Some seasonality in terms of the week, but also seasonality in terms of, is it winter, is it summer? So here we have a data set of the total load. This is the actual energy usage in each country at noon on each day from January the 1st to I think December the 10th. I chose noon just because I didn't want various things to interfere. You know, you've got midnight would feel strange, and if I was to pick certain times in the morning, then nautical twilight would affect it, etc. So sticking with noon. And as mentioned, we've got all sorts of seasonalities to correct for, and it's not immediately obvious that this sort of downward surge in energy usage that we're seeing in March is due to the pandemic or seasonality or a combination of the two. So it's useful to have 2019 data there to correct things with, and that's certainly something that we'll have done in the background by the next time you sort of see a plot like this later in the talk. All right, so here is what the data sets look like for a number of European countries, not including the UK now. And what we've done here is just done a very simple kind of constant with discrete jumps model for each of these 16 countries, but also incorporating whether we have bank holidays, because they have a huge effect on this data set. So for a country like Austria here, we can see that we have some pretty large jumps in the energy usage in our sort of blue idealized model, which roughly conforms to what we're seeing with the red, with the actual. I should mention this red is a log plot produced by one of my colleagues. And this is just something that's taking into account when the MPIs took place. So this blue line here is this jump here is just precisely when Austria went into lockdown. And you can see that this makes some intuitive sense with regards to explaining the data. But we'd like to be a bit more concrete about this. In particular, we would like to try and understand what's going on with models with respect to stationarity in the signal with jumps. And that's where thinking about change point detection comes in. So I thought I would briefly talk about a new method for detecting change points in multivariate data of the type we're seeing here, and how we might use that to try and inform the particular questions of interest with regards to the COVID and the economy. So what is a change point? A change point is simply a point in time at which something changes. So it might be a change in mean, a change in variance, a change in mean and variance. It might be a change in rate if we're thinking about exponential data, for example. Anything which sort of materially affects what we might reasonably observe. And this has been an area of interest for some time, although it's only really been in the last 10 years or so that we've seen a kind of explosion of interest, and we've had a number of methods arriving to sort of answer many of the questions in the big data era, if for want of a better phrase, that are linear time, but typically have been focusing on the univariate setting. So it's only in the last few years that we've seen methods that are deliberately trying to be usable in the big, in sort of big multivariate data contexts. So more on that in a moment, but first of all, I just want to talk about the data picture that really inspired me to start thinking about this, and this is informed by global terrorism. So there's a preprint with regards to this project on arXiv if anybody is interested, but really it all starts with this picture. So this is a map showing where terrorist incidents have occurred since the beginning of 1970. And this is given by the National Consortium of the Study of Terrorism and Responses to Terrorism, or START, and they're affiliated with the University of Maryland, to whom the database is copyrighted. And I saw this and I wasn't really surprised. It was, it was fairly intuitive to me as to why certain parts of the world were seeing, over this very long period of time, more terrorist incidents than others. What I was more interested in was the evolution of this over time. So, for instance, if I was to ask a question like, how has the probability of a terrorist attack changed in a given country or a given continent or even worldwide since 1970? It's not immediately obvious from this plot as to how I might try and answer that question. Before I get into that specific problem, I just want to give you a little bit of context for the GTT. So as mentioned, it's a collation of terrorist events since the beginning of 1970. There is a year of missing data. 1993 is missing, and this is due to an office move that was made in 2001. It goes up to the end of 2017. There are more recent data, but you do need a license. So again, with regards to open source data, 2017 is sort of the most recent year you can easily have access to. And as mentioned, it's copyrighted to the University of Maryland. And the big question really with these data is what defines a terrorist incident? What allows it to be included within this database? So in addition to involving violence committed by a non-state actor, which feels sensible to me, at least two of the following three criteria must be satisfied. So we must have some goal, which is political, economic, religious, or social, which is informing the act. And with regards to an economic goal, it can't purely be for the profit of the group. So it must be some wider economic goal. For the second criteria, we have, I think, something that feels intuitively quite sensible. Evidence of an intention to coerce, intimidate, or convey some other message to a larger audience than the immediate victims. And this sort of feels, as mentioned, quite intuitive. This last one was a bit strange to me at first, but reading around the description of the data on the University of Maryland's website sort of makes more sense. The action must be outside by the parameters permitted by international humanitarian law. And I asked the question I thought was reasonable was, when was the last time I encountered a terrorist incident that was inside the parameters permitted by international humanitarian law? And the answer is that this is here purely to exclude sort of acts committed within warfare. And I guess they just want to avoid the quagmire associated therein, which is reasonable. So I'll sort of park that for now. So that's just to make sure we're all on the same page with what is being referred to as a terrorist incident here. And I wanted to go back to the question, revisit the question of how do we look at the evolution of terrorism probability over time, and sort of turn this spatial picture we had into a temporal picture. So here is a graphic showing the regional stratification of the GDT. What do I mean by this? So each incident is given an identifier in terms of where it took place, which country, which region, exactly what happened. And the region information is quite useful, I think, because, well, we can naturally categorize an incident as happening in one of the 12 regions: North America, Central America, South America, and so on. Again, these are all political definitions given to us by the GDT. I've not, for example, defined Mexico as being North America. It's just defined that way for the database. I've chosen regions rather than countries purely because country boundaries can be quite fluid. So, for example, if we think about Germany, given that we're thinking of 1970 onwards, there might be some confusion as to exactly what to do with East Germany. This sort of eliminates that. Obviously, I recognise it's not entirely perfect, but again, it's trying to overcome these country effects. But again, I accept a country-wide inference might be quite interesting. So pick your favorite region, remember its color, and what I'm going to do on the next slide is show you what the evolution of that particular region looks like over time. So I'll just pick the Middle East and North Africa, just because it's right in the center of my page, and it was in black. And as you can see here, the evolution of the number of terrorist attacks is quite striking. So this is a count per month since the beginning of 1970 of each of the 12 regions for basically the last 50 years. And it's pretty striking. We can see straight away, almost by eye, that we've got some points in time where we have a surge in the probability of a terrorist attack, it seems. And this actually corresponds to the Arab winter, which is the term that sociologists are increasingly giving the period after the Arab Spring. And I feel like I could have said something like that before I saw this picture, to be honest. And certainly now that I've seen it, I don't need a sort of fancy change point model to come along and tell me that I'm sort of what I can see with my own eyes. So it really invites the question of what's the point, so what? Well, I have a bit of a problem with this. The first thing is, while it might be relatively straightforward to see, for instance, a local change, let's say, so a change that just occurs in, say, Central America or the Middle East, it's less clear as to whether we have a global change going on. That's what I mean by global change. Essentially, for this context, I mean a change that affects a number of regions at the same time, or that the model can reasonably label as affecting regions at the same time. And it sort of intuitively feels like these should be here. So I hear from the media all the time about how certain events are, increasing the probability of a terrorist attack all over the world. And so it intuitively feels like they should be present over the last 50 years. So I really want to be looking for both local changes and global or universal changes at the same time. But just rewinding a little bit and thinking about how the GDT has been used in the past with respect to change points and change in policy, which is ultimately what we're interested in with respect to thinking about COVID and the economy, very much has been used in this context in the past. So if we're thinking about Northern Ireland, Lefree, who is one of the principal investigators on the GDT to this day, looked at 6 particular policies enacted by the British government between 1969 and 1992. And actually 5 of these policies led to a backlash and what didn't turn out to be a deterrent effect at all. I'm happy to discuss why a little bit if anybody's interested in that. In addition, a slightly more recent paper looked at using a hidden Markov model to specifically look at the activities of the FARC rebel group in Colombia between 1998 and 2006. And this was actually a day-by-day thing rather than thinking about a month-by-month count as we have done. And they found that it was a significant change from the end of June 1998. And this was due to funding, quite significant funding put into the country from the US to combat the drug economy. And this, by all accounts, was extremely successful. I think there was another conclusion later in the paper which said that when this was alleviated a bit, when the funding was lifted somewhat in 2000, there was a steady increase in violence. So maybe not the happiest of endings, but certainly it was better than it was in 1998. Okay, so we have some local analyses that have been taken into account, but as mentioned, we have this problem of local inference versus global or universal inference. So we have this picture on the right here, this change, which is what we might call a local change, or I'll call a sparse change. So in this case, we have a change that is sparse in the number of variates. So it's a change that only affects a very small number of the variates within a large variate system. And here I appreciate that 4 is not a large number, but I have a distinct inability to draw slides with many variates at the same time. And on the right here, we have a universal change, or what we might call a dense change. So this dense change is affecting most, if not all, of the variates in the system. And we want to have good statistical power to detect both types of change. We want to be able to essentially detect very dense changes that are nonetheless subtle in all of the variates, because if there's a minor shift in, say, the probability of a terrorist attack all over the world, we want to be able to detect that. But we also want to be able to detect, with good statistical power, changes that might be more localized, but may well be significant. And historically, recent change point detection techniques tend to be more powerful in one setting than the other. So if you have a competitive method in the dense setting, it's unlikely to also be competitive in the sparse setting, and vice versa. So I'll just talk about very briefly some of the existing methods that tend to prioritize one setting over the other. They all use something called the Q-sum transform, which is based on this test statistic. So this is just for a single data sequence rather than thinking about a multivariate data system for now, yj from j1 to n. And the test statistic is just based on taking means about a putative change point. And if we were to, for example, have a synthetic data series here with change point at time t equals 500, then we would discover that the value of the Q-sum at t equals 500 indeed maximizes the Q-sum test statistic and is above this red line here, which is given to us from theory. So we would declare a change point there. In many ways, this is quite simplistic. So in particular, this is can really be applied to the Gaussian change in mean setting, but it also has some model versatility, which I'm happy to go into with questions. So what many methods have sought to do is to extend this to multiple variates by aggregating the Q-sum test statistic across essentially, instead of having yj, we now have yij, an extra index, and we just want to aggregate these wit in a sensible way to try and have power in either the sparse or the dense setting, or both ideally. And there are 4 ways of doing this that I'll talk about. I'm sure there are others. So there's this way of just basically saying, let's calculate the mean of these things. And this is most powerful in the dense setting. And this is quite intuitive because if I've got something that's changing slightly in all of the variates, then if I were to take the mean of these, then that mean is preserved. The mean preserves this little change in all of the variates. So this will be powerful in the dense setting, but less so in the sparse setting. And it's the situation is precisely reversed if we were to take the maximum of these Q-sum transforms. So in this case, we're throwing out everything except the most significant looking thing. So essentially, this is perfect for the situation in which just one thing is changing, but if everything's changing by a little bit, then the largest thing of a lot of little things is still a little thing. The method which is actually quite nicely balanced is this method of Cho and Prislovitz, which is this what I've called the binary weighted method or bin weight method, but they christened sparsified binary segmentation. And despite sort of sparse being in the title, I think it's sort of the most nicely balanced of all the methods that was sort of previously in the literature. So essentially, it tries to be a matchup of mean and max by throwing out everything that doesn't look significant, but also taking a weighted sum, binary weighted sum, literally, of those things which are significant. And as we'll see from some of these simulations later on, this is really quite a nice method. And then we have the inspect method, which again is a sparse projection optimizer. I'm not going to write down the closed form of this because, well, it's quite complex. But again, this is useful in the sparse setting, but in practice you can use it in either. Okay, so the issue really is what happens if we have a different change point problem. So I've talked about Gaussian change in mean and how QSUM essentially sort of inherits this Gaussian change in mean problem. And you know, typically, if we choose something that's well outside the Gaussian change in mean wheelhouse, then we might have QSUM resulting in low detection power. Not always going to be the case, but we run that risk. So for something like, for example, the Global Terrorism database, we have discrete data. So it makes sense to try and think of something which has more versatility. So a very common approach is to take a cost function and try and minimize it. So don't worry too much about this equation. Essentially, the bits we need to be interested in are we have some cost function, a segment cost function here, that we're trying to take sums over an unknown number of change points, where we're trying to estimate these change point locations. And this segment cost function, as mentioned, is going to be something that is more model based. So for example, we might choose a likelihood. So if we suspect we have, for example, a Poisson likelihood or a negative binomial likelihood, if we're thinking about count data, we can write down a cost function quite easily based on that. We also need some regularizer, some penalty, just so that we don't overfit. So this is for, if you'll notice, a data sequence again. What happens if we try and extend this to a multivariate setting? I'll try and whiz through this because I'm conscious I want to get to the COVID. So this was extended to a multivariate setting in which we have a penalty for introducing a change point, but we also need to add on an additional penalty for complexifying a change. So we add on a penalty of alpha for each variable that we label as affected by a change point. So for this change point here, we have a penalty of beta because we're introducing a change point, and an additional penalty of alpha twice because we have two things that are affected by the change point. And ditto for this change. I clearly wasn't very imaginative when I set up this picture. So we can set up a cost function, uses two penalties. It's highly inefficient if we try and minimize this using, for example, dynamic programming. We really don't want to be doing this. It's effectively order n to the 2d minus 1. Change the GDT example has d equals 12, and so that's n to the 23. I'm not planning on living that long, so let's see if we can improve this. And we can actually improve this by sort of thinking philosophically around what the QSUM is doing. So the QSUM is effectively giving you a specific saving in the Gaussian change in mean setting. So we can generalize that to thinking about a saving you get from taking differences in cost functions. So the difference in the cost function we get here, which we'll call DIT, which is kind of analogous to the WIT from the earlier slide talking about QSUM. It's the cost of having no change at all versus the cost of placing a change at time t, which is precisely what the QSUM was, but specifically for the Gaussian change in mean setting. And what we can do is we can combine these savings using a kind of very similar idea to Chohan-Prisovic's idea, which was this, if you remember this censoring, anything that's above alpha will keep, anything that's below alpha will throw out. Very, very similar idea to that. We have a sparse saving here, and we'll have a sparse part of our test statistic and a dense part of our test statistic. And whichever is larger will declare as being the change, essentially. So if this whole thing is greater than 0, then we'll declare a change. And then we'll just look at whichever one's larger and say, if that one's larger, it's a sparse change. If that one's larger, it's a dense change, or local and universal if you prefer. And we call the use of this test statistic inside the method that we have subset, which stands for sparse and ubiquitous binary segmentation in efficient time. If you're wondering why I didn't call it sparse and universal binary segmentation, which would be a much more or much less pretentious name, it's because it didn't occur to me, which probably says more about me than it does about the world as a whole. But there we go. So that is the background for what our method subset is doing. Here is a plot which shows that it works quite efficaciously with respect to many of these existing methods. As mentioned before, the sort of method which appears to compete best with it in both the dense and the sparse settings is this binary weighted method of showing crystal bits. The others either seem to want to prioritize one situation over the other. So this is just a plot showing that we don't require too much of a change magnitude in the Gaussian change in mean setting in order for us to really start detecting this change in all situations. So we have here a dense setting in which everything's changing, 1,000 variates. Here we have a more sparse setting, 50 things are changing, 1,000 variates. And here we have very few things are changing, just 5. And again, we don't, relative to the other methods, we don't need to have too much of a change magnitude to be able to detect things. Okay, so this shows that we have competitive statistical power compared to these other existing QSIM methods. Let's talk about using it in the GTD. And here we chose a negative binomial likelihood. This just gives us some flexibility to model over dispersion because we have 2 parameters in the negative binomial likelihood. So we'll be thinking about looking at the change in, well, the standard nomenclature is the success probability, which feels a bit tasteless given that our particular example, but hands are tied a little bit. So here we're just thinking about the probability of a terrorist attack. How does that change? And here is what the picture shows us for the GTD. And yes, it appears that most of the changes are sensible. I just wanted to flag up this Arab winter change again. You can see that this change here sort of picks this up. There is a secret hidden post-processing layer to this subset method I've not talked about. Before that, you have something which is sort of clearly demarking this as a single regime in which we're moving from one situation to another, but not necessarily abruptly. And this sort of gets pruned out a little bit because we want to be more parsimonious. But it is detecting that this is kind of an odd case in which we've not got an abrupt change. Just wanted to flag that up. The other thing of interest here is that most of the changes appear to be sparse. Most of them only appear to be affecting one region, with the exception of this change in 1998. What's going on? This is January 1998. Why do we have a change in these 3 regions? And if I show you some other regions here, we have Australasia and Oceania, Central America and the Caribbean, South America. Again, the change is happening everywhere. What's going on? I got really excited. I thought this was all part of, Francis Fukuyama said in the 1990s that it was the end of history. And I thought, yes, we're seeing this here. We've matured as a species. Turns out it's not the case at all. It's nothing to do with anything going on in the world, at least not obviously. Basically what happened was in 1998, the definition of a terrorist attack was changed by the compilers of the GTD. So I lied to you slightly before. So that this definition of a terrorist attack that I showed you before has only been in place since the beginning of 1998. Before that, there was a slightly more fluid definition, and this led to clearly a change in what was being picked up and what wasn't being picked up. So this is useful actually. So I was initially disappointed, but it's a sanity check on the fact that most of the change points that are here in reality are in fact sparse. We're not seeing dense change points throughout this 50-year period, which is I think quite a useful bit of analysis because it sort of goes against my own intuition of what I thought I should be seeing. So most of the sparse change points I can see can be explained by, for example, the beginning of, in Central America, the beginning of a period of civil wars in a number of these countries, a number of civil uprisings. And the last one in Nicaragua, I think, ended in 1992. That's the change you're seeing there. Okay, and here is just a summary of that information. If anybody would like to ask more questions about that at the end, I'm happy to try and answer questions, although I'm certainly not a historian. All right, so clearly we're all here for COVID. And so I wanted to talk a little bit about how we used subset in the COVID context. And here it is on the Entsoe energy dataset, or the information provided by the Entsoe transparency platform. So this is for 9 countries. We looked at, as I say, sort of about 20 plus European countries, all those for which we had a significant amount of data. And the name of the game here was really trying to normalize the data we had with respect to 2019 and the very beginning of 2020. I think we just used January 2020 because sort of the earliest policies that were being enacted in Europe, as you saw from the Blavatnik dynamic from before, was sort of introduced in the last week of January. And in the UK, interestingly enough, if I were to superimpose the stringency index on the background here, we can see that many of the changes that we found do appear to align with changes in the stringency index or the strengthening of NPIs, particularly as we were going into lockdown. Indeed, One of these changes conforms almost to the hour as to when Boris Johnson made his speech on the 23rd of March, instructing to stay at home. So this was quite exciting. And indeed, the more we sort of plumbed into the data with respect to many of these other countries, it was clear that we were actually picking something up that was almost directly aligning with these massive changes in policy. So this wasn't necessarily telling us something per se about the economy, but it was saying something, I think, about the fact that our assessment that this was appropriately proxying the economy might be an accurate assessment, which was useful. And it also conformed with what the Cabinet Office felt a priori. The other encouraging thing from this picture is that, obviously we were thinking about this at the beginning of June, was that we were seeing that certain countries that were somewhat ahead of us in terms of the pandemic and relaxing these MPIs, had some success in seeing a bit of a recovery in the energy usage. So in Spain and Italy, probably most notably, we can see that by lifting some of these more stringent restrictions, there was some pickup in the normalized energy usage. And I stress here the normalized energy usage is again on a log scale. It is just a more useful scale to use for the energy data. I'm noticing some questions in the Q&A. I'll do my best to pick them up during the next lull, I promise. The dense change point that I want to flag up here is on the 5th of April. So I'll just sort of move on to my conclusion slide for this specific part of the analysis. There was more on subset, but I didn't want to make it completely subset focused. So most of the change points are again sparse, as we saw in the GDT example. There is evidence of, I think, what we might call lagged sparse changes. So what do I mean by this? So I didn't want to overburden you with too many plots with horizontal lines, vertical lines. But if we alter something called the minimum segment length, that is sort of the distance between in time between successive change points, then what we see many more dense change points as we'd expect, occurring almost at the same time. Whereas the plot we saw there had quite a small minimum segment length, so it allowed changes to occur quite close to each other, be they sparse, be they dense. And this is suggestive of the fact that we're seeing a lagged sparse change effect, given that the epidemic, of course, did not affect all countries at exactly the same time in the same way, and therefore MPIs were not introduced at exactly the same time and in exactly the same way. Now, there is a dense change point on the 5th of April, and I've been racking my brains to try and work out what this is, because this does not conform to any obvious change in MPIs. It also doesn't seem to conform to a continent-wide weather change. I've checked this as much as I think is reasonable, but if anybody has any theories on the 5th of April, I'd be very, very interested to hear them. Certainly in the UK, the 5th of April sort of makes sense because it's the end of a tax year. And at the time, I think that it was the day of the Queen's speech. So it's sort of it's a somewhat meaningful day, but I'd be interested in hearing why it seems to be affecting many, many countries. And this point about relaxing MPIs, as mentioned, it certainly appeared at the end of June that those countries that had been starting to relax things already did appear to have an instant, but obviously very clearly asymmetric economic effect. You can tell which A word is on my mind today. Okay, so that's everything I wanted to say about subset, but obviously this wasn't the whole story with regards to what we were doing with the Cabinet Office. So I'll just talk about a few conclusions that may be of interest to people. So we looked at reformulating things as a regression, because essentially if we're thinking about the change point detection model that we had there, using subset, so the subset model we were using there was, again, Gaussian change in mean and variance. So thinking about clear heteroscedasticity, but also these changes in signal that I was discussing right back at the beginning. So, if we're using a sensible penalty there, like an L2 penalty, there's some clear equivalence there between standard regression. So we looked at a regression analysis incorporating energy usage from Entsoe, but also all the different types of mobility that, as discussed in Rito's talk, may potentially be useful in informing exactly what's going on with respect to the individual impacts of specific NPIs. So we used an elastic net and essentially allowed the model to try and fit the sort of optimal weights to reduce noise as usual. And here is what we saw for some of the policies. So the UK is represented by the red circle, all the other European countries by black circles. So this is the percentage effect of restricted gatherings on energy, retail, grocery, parks, transit, work, and home mobility. So it's very clear that by restricting gatherings, there's some overall negative percentage effect going on in the UK, at least, in terms of what that does. Meanwhile, if you restrict gatherings, clearly we're spending more time at home. So this feels sensible. Clearly, there are some outliers. There's some multiple test issues going on here, and that's something we can chat about, I guess, in the panel session. Here we have restricting internal movement, and again, people spend more time at home. This shouldn't come as a surprise. But again, for the UK, it was interesting. This specific policy was sort of not seen as something that was significant. Again, obviously, the elastic net has some willingness to let things go to zero when perhaps it shouldn't be quite so brutal. But that was simply how the things were set up there. Here we have the stay-at-home percentage effect, and it shouldn't be a surprise that more of us spending time at home. Interestingly, there were again a few outliers. Again, I'm pretty sure this is due to multiple testing problems, but on the whole, this appears to be sensible. The percentage effect on energy here is small, but clearly significant. And again, we have some covariates that are clearly not useful. So for example, if we're thinking about the stringency index, as mentioned, the score from 0 to 100, which kind of meshes everything together, the model in general will make this 0, again, up to a few countries. So the main purpose of this was not per se to try and drill down exactly what was going on with each specific policy, because we felt there wasn't really enough information to leverage from this, but more to try and work out a model of which countries we should try and emulate coming out of the pandemic. So this analysis was carried out for 26 countries separately, including the UK, and we looked at a way of effectively ranking each of the countries based on these outputted covariate vectors. And so we have a list here of most similar to least similar to the UK in terms of how they seem to be lying in the MPI effect space. Treat Luxembourg with a bit of caution for various reasons. There are some difficulties with how Luxembourg should be treated with Germany in the Entsoe data set. But France is way up there, as is Ireland, and as we potentially all know from the second wave of the pandemic, France has sort of been a country that we've emulated in more ways than one. So this feels semi-sensible. On the other side of the equation, countries like Greece and Italy and Sweden are really not countries that sort of the UK is similar to in terms of this MPI effect space. The very last thing I wanted to talk about, which sort of goes back nicely to what Rita was saying, and hopefully I've got enough time, is looking at the energy data in isolation again, but thinking about trying to relax this assumption that we have a linear dependency on policies and effects. So here we used a GAM, and we're thinking about the effect of individual policies on energy usage in, first of all, the UK, and also various other aspects of the pandemic. So this is just looking at the number of deaths per day, and how it affects the overall energy usage in the UK. And again, this is normalized, so these log normalized. So these 0.2 shouldn't be taken as the number of megawatt hours, for example. And just to recall that the Blavatnik data set gives you a score from 0 to 4. So a score of 0 is something that is, schools are entirely open. A score of 4, schools are basically entirely closed. And we can see from this that schools seem to be having an interesting effect on energy usage. Seem to be having a almost disproportionate effect on things. So I'm just showing you some of the policies here. I could show you more. And this is interesting. Again, I had a quick look at some of the other countries. I'll just remove this bottom right plot. Hang on. There we go. This is for Ireland, which again I mentioned was sort of seen as being quite similar to the UK from our sort of back of the envelope elastic net calculation. And you can see here that there's the same sort of effect in terms of schools. It's sort of having the surprising effect on energy usage. I sort of twigged at this point and realized, aha, hang on, we're carrying out this analysis in June, July. Most of these countries have had schools closed since March. So is the model effectively scapegoating this this parameter, this schools being closed parameter? And the answer to that is probably yes, but it is interesting exactly how many countries are taking this as the scapegoat policy. So we're seeing here in Spain a similar sort of effect. Sweden did not entirely close schools, so they only ever got as stringent as a 2. But again, we're seeing the same sort of thing going on. Here's the Netherlands. And as at this point that I thought, well, this surely can't be too much of a coincidence. But then France turned up, and France is the note of caution I would give to the sort of hypothesis that says, you know, closing schools has this sort of very, very detrimental effect on energy usage and therefore by proxy the economy. So France had opened up the schools somewhat prior to the beginning of the summer holidays, and you know, it's clear from this model that it's not as entirely simple as many of the other countries were telling us. But nevertheless, this is something that we fed back to the Cabinet Office with respect to schools, seemingly having this interesting effect on the energy usage and the economy. This was, I stress, after many statements with regards to the opening of schools in September had been made. So we are one of many voices contributing to the discussion on this. So this certainly shouldn't be seen as the be-all and end-all as to, for example, why schools are open now. But it was an interesting observation that we made. And again, there's this interesting other side of the equation with respect to what Rita was talking about and opening schools and number of cases and so forth. So just wanted to summarize, we've used change point detection and a number of other techniques to think about exploring the relationship between policy change and, for example, national energy usage. We've tried to directly model the economy using open source high frequency data, but this is certainly easier said than done. And we've, as I say, tried to come up with a ranking of countries that the UK might be best placed to emulate going forwards, or certainly this was the case back in June. So I will stop sharing my screen and I shall very happily answer any questions that you've sent my way.
Oh, thank you very much, Sam. That was great. Very interesting. So I see a couple of questions in the Q&A. So could this be scaled down from countries to counties for the tier system that's currently in place?
That's an excellent question. So with regards to the mobility, the answer is yes, or yes asterisk. I've not actually gone and checked to see where these specific Google mobility series conform to the regions in which we have tiers defined. But I think in principle the answer to that question is yes. With regards to the Entsoe dataset, I think the answer is no. So in general, that's a national picture. There are some exceptions to this. So for example, if you're thinking about Italy, the Entsoe energy dataset gives you the usage across, I think, 5 or 6 regions. But I'm not sure these regions are terribly helpful at sort of demarking separate policy areas, for example.
Yeah,
that was a little bit annoying. So yes, Will touches on a really interesting point there that there are sort of issues with trying to localize this, and this might be an interesting lesson for future pandemics, is to sort of formalize or sort of join up thinking between data collection and policy decisions somehow, because I think that has been a little bit exposed, in my opinion. So hopefully that answers the top 2 questions.
So the next question is about statistical significance. So what does it mean for your model to declare a change point? I think that's what's being asked. So if the null hypothesis is that the data follows a whatever distribution, the probability of seeing an effect of magnitude y is at most z. What would this be? What would be a natural choice, sorry, for the underlying distribution?
That's an excellent question, and it sort of gets back to something I alluded to very, very briefly in the talk, or possibly not, this is possibly during practice, which is that basically, as mentioned, sort of ad hoc after I had the picture up, so this maybe wasn't very helpful. The exact modeling assumptions we were using subset under were that we had a Gaussian change in mean and variance problem. And effectively, that just reduces to using quite a complicated QSUM in the background where you have sort of appropriate normalization. So you normalize by a random thing. So in that sense, you can use a version of Wilkes' theorem to give you some form of penalty, which effectively you can backtrack to give you a p-value. So here we were using a Bayesian information criterion for that, which hopefully I feel makes empirical sense. The only way in which it wouldn't make sense is if we had lots and lots of heavy-tailed data. And there is a risk of that, I suppose, because as mentioned, we have this bank holiday problem where you have really quite serious anomalous results. So you might have seen from that first plot that was produced by one of my colleagues that you had these sort of significant downward spikes on energy usage on those days. And if you have a lot of those, then that is an issue for using the Bayesian information criterion. So one thing we tried to do was, this took a long time, but I went through a library of upcoming bank holidays and basically said, right, we need to introduce these as additional covariates and use these to try and standardize the model. I won't get into it because it's, well, life's too tedious. It's an end to the 23 problem, let's put it that way. But it was something I tried to take into account. But yes, I very much take your point, sort of putting your finger in the air and saying Gaussian change in mean and variance has its issues as well.
The last question for Sam before we bring the panel back. So would you say that the methods that you discussed and that Rita Bretta discussed make modeling lockdowns and waves of COVID stronger? And why do you think that?
That's a very good question. I feel like that might be a good discussion question for the panel as well, but I'll give it a quick go now. Okay, modeling lockdowns and waves of COVID, and why okay. So I think almost partly, so part of the equation here is, again, the nature of data collection getting better. So if we look at the Google mobility is a great example. In the first wave, we had data from the 18th of February, and whether you think that's a sensible date or not is a debate in itself. I'm not sure it is, because already by then you had public information campaigns against COVID. Now that we've been collecting that for months and months, it's clear as to exactly how that evolves with under certain sensitivities with respect to policies. So basically, it enables us to build up a greater picture of what's going on. So I think partly that's why is that the data picture is just naturally more complete. I think naturally as well. Yes. I certainly feel that I have a slightly better grasp on assumptions which are and aren't sensible. So a priori, if I'd not taken into account bank holidays, and as I did initially and got something that looked completely messy, it would have been a little bit foolish, to put it mildly. There are still things that I really have no clue about, like the 5th of April. If anybody can explain the 5th of April to me, I would be extremely grateful. Yes, sorry, that's a bit wishy-washy, but fundamentally, I think it's a question of data, and hopefully going forward, this is something that I think should be the main lesson from the pandemic.
Okay, thank you very much.